Now it's the turn of Dave Cheng. Unsimpai Dave Cheng is a senior deep learning researcher at Qualcomm AI Research. He received his PhD at Duke University, advised by Professor Iran Chen. His research interests include automatic machine learning, AutoML, neural architecture search, quantization, and on-device optimization. Thanks, Dave. Please.
Thank you so much for introduction. Yeah, I'm very excited. I am Xinpai Dave Chen from Qualcomm AI Research. I'm very excited to be here to share you our recent progress at Qualcomm AI Research. In Qualcomm, we have been conducting tons of research regarding AI model efficiency. Since we're producing chips, we're making sure that our models can be shipped directly on the chip and also be deployable for users. So today, due to time limit, I'm just going to cover a small portion of our research. So title is Automating Model Optimization for Efficient Edge AI from Practical Solutions to Open Source Toolkit. And today's agenda, I'm going to cover, again, neural architecture search, but we are doing more hardware-aware searching that we plug in Snapdragon-related hardware constraint in our searching. You can plug in other hardware constraints as well. It's an automatically searching method, and after that, we are going to talk about how do we do automatically quantization based on our found architecture. So we're making sure that the model can be very memory efficient. And after that, we're going to talk about how do we boil down our techniques into open source toolkit on GitHub that you can directly use our source toolkit and also our already trained Model Zoo to prevent CO2 emission. So let's take a quick look of the challenge of AI model workloads. I know previous talk has talked about that a lot, but in IoT devices, we are making sure that our large model, which is computation intensive, when we want to ship that to IoT devices such as MCUs, it usually have to be run in a long battery life at all time. And also, sometimes, as mentioned from previous talks, that the memory storage and bandwidth is a limitation. So in order to solve that, Qualcomm has been doing a holistic research on that, including quantization, compression, neural architecture search to compilation. And let's talk about neural architecture design first. So existing NAS methods solutions have many problems. For example, some of them are lack of diverse searching space. For example, they're only searching certain operations or certain activation functions. And also, NAS is not very startup friendly. For example, it requires hundreds of GPU times to fine-tune the final results and also training. So it cannot be very portable for end users somehow. And another thing is that after you've done the searching, it is hard to scale down to a small amount of a computation constraint as well. And also, even though current NAS community has been trying to combine hardware constraint on the searching, but most of the hardware constraint are proxy. It is not a real hardware constraint there. So here we present you DONNA, that we solve all these problems at once. First, we provide you a much bigger, diverse searching space with the best model with given search space, and also it's really low cost. It can be done in 2 GPU days by 1 to 2 GPU, and it also can be scalable to end devices such as IoT devices. And we have a much accurate, reliable hardware measure simulation during the searching. So we're making sure that the search model can be delivered on target. So let's give you a quick workflow explanation of what we do here. First of all, DONNA Distilling Optimal Neural Architecture, we firstly let user define a search space. This search space can be a neural architecture backbone. And user can define their own parameters, such as convolution kernel size, expansion vectors, so on and so forth. So user only need to provide these two, and we just have a plug and play end-to-end searching for that by starting building an accuracy model via knowledge distillation for each blocks. And then we use evolutionary searching, search based on the hardware constraint, and then eventually fine-tune the found architectures. And let me dive into deeper of each of the bullet points here. So for search-based design, for example, if it is a backbone model, as shown here, usually we try to, because like the backbone model is huge, we chop down the model based on the output feature map size to different chunks. And so for example, in this example, we have 5 different chunks. And our main goal is to, instead of directly pruning down such model that might cause underfitting of the data, we try to build a much smaller network that can mimic such teacher network. So you can consider that a given network is a teacher network, and we are trying to use smaller blocks, trying to mimic its function. And so in the neural architecture side, we're trying to firstly build such smaller modules that can do the same thing as teacher model. And the user just can only just choose what the search space they want to have. For example, they can choose the kernel size, they can choose activation, or they can choose all of them. And after you choose the search space, you have you have given what you want to search on, and you start to build this block library, which means that we try to measure the MSE loss between each of the blocks, and we try to find out which block can mimic the best of the teacher blocks. And by giving this such teacher library, we will be able to use this library to train our accuracy predictor to predict which model performed the best. And so after you build such accuracy predictor, I have to mention that the accuracy predictor is parallel to your hardware constraint. So after you have a accuracy predictor, you have your model definition and its predicted accuracy, but you don't really know what it performs on each of the hardware constraint. So you can plug in any of the hardware constraint here. For example, here we plug in Snapdragon hardware constraint using our own simulation, and the simulation is pretty close to the real hardware. And each time while doing the evolutionary searching, we sample the predicted accuracy and also the architecture and its corresponding hardware measures. For example, its latency and memory constraint. And by doing so, we have a wide spectrum of models from low cost to high cost. And we try to find, and eventually we fine-tune the search architecture with a given teacher network. So the small network can have a very close accuracy to the teacher network. And therefore, eventually, what we ship to the user is a bunch of wide range of architectures from low cost to high cost. And comparing to previous works like once-for-all networks, DNN, MNSNet, we show that DONNA can provide you a block level granularity, a much more diverse search space, and also a considerably good search cost that can be easily reproduced by end users. And other than not just the cost-wise, it can be expanded well to different kind of tasks. For example, from classification to object detection, even depth estimation and image denoising. We've been showing that we have gained latency from 25% to 45%. Let me give you a more practical example of what DONNA can do here. So if you have a state-of-the-art depth estimation model already built on your device, and somehow this SODA model performs well, but it doesn't perform real time, and you want to improve the latency of the throughput so you can have a more real-time solutions. Here we directly plug in DONNA in this case, And we show that we provide a very similar accuracy as our baseline models, but have like about 40% higher frames per second throughput, and that has basically no accuracy loss. If you have been to our booth the past few days, you've probably already seen this demo on Snapdragon-based mobile phone. And so besides the model definition part, model crafting part, a lot of time in the systematic level, the bottleneck could happen at the data transfer. For example, the data transfer between data and your execution. So that makes model quantization and compression more important because it can first save memory usage. The last time you execute on the chip, the less power you use, and much latency between data transfer and also smaller silicon area. So let me give you a brief review what quantization does, and then we go to what Qualcomm provides as a solution. So what neural network quantization does is that given a neural network such as the already search architecture that we mentioned before, we can quantize that with weight quantization and also activation quantization. So in the calculation time and storage time, we have trimmed down the storage. So it provides the benefit that I mentioned above previously. But somehow it has some drawback, which can be kind of analogy at the right figure here. For example, if you have a 24-bit pixel of 24-bit of pixel of image, it shows like a much more informative image. But if you quantize that to 8-bit, you will lose certain information, and if you go down to 1-bit, it can only provide you grayscale images. And therefore, that have a direct impact of your inference time. When you have from floating point 32 and trim down to integer 8, you might see some inaccurate segmentation result. So I'm gonna talk about what Qualcomm did here. That is, we provide AIMET and AIMET Model Zoo to solve this problem, and it's open source. What AIMET do is that we provide a quantization scheme, which is automatically do quantization for you. That you don't need to learn how to do quantization. It's just a hit and run button, and it comes with a compression and visualization tool that you can see the sensitivity of each layer component. We have many kinds of quantization in AIMET, but let me just give you one example of AIMET. So one of the tools in AIMET is ADA round. So you might know that if you have a floating point weight, if you want to quantize that to 8-bit, which is ranging from -127 to 128, which is integers, right? So when you mapping a floating point to integers, the most straightforward idea is having a really low reconstruction loss between the quantized weight and the floating point weight. So it's called rounding to nearest method, and we noticed that it is very intuitive, and it might work. But somehow, when in certain tasks, for example, object detection, this kind of rounding causes a huge accuracy degradation. For example, from 82 MAP to 49 MAP, and here Qualcomm provide a so-called ADA round, which we're not just arguing the reconstruction weight between between the quantized weight and also the floating point weight, but also we're trying to learn where should it round it to. Instead of rounding to nearest, if we can round it to other side of the bin, and if that can provide you a better result, and at the end we still preserve the quantization. So here we show that by using ADA realm, we can have a much better quantization result, which is really close to the floating point result. It's only 1% MAP drop, and therefore, in the real world situation, it can provide you a much more accurate object detection result. Right, and ADA realm might sound very domain knowledge specific solution. So in Qualcomm, we have AutoQuant, which is that we provide a sequence of quantization optimization, and the end user just have to provide a model definition and the tolerance of accuracy degradation. They only need to provide these two, and AutoQuant will automatically find out the best quantization solution for you. And the output of the AutoQuant is an analysis report that telling you what kind of operation is more sensitive to quantization in your network. And also, we provide the best quantized network for them. So AutoQuant is a push button solution that the network can directly go into BN fold, or Bayesian folded, and then we analyze if we should do cross-layer equalization and ADA round, or even mixed precision in this model. And this is a whole sequence of optimization. And so this is, I think this is a more practical solution that end user doesn't need to think about, like what should be learned. And therefore, if you use AutoQuant in our solution, which shows that in our AIMET quantization, it has a much more accurate segmentation result. And we're not hiding recipes, and we're providing model zoos on both TensorFlow and PyTorch, including all kinds of tasks from MobileNet, EfficientNet, SSD to PostNet, and also GANs-related architectures. And at the end, I hope you guys can just take advantage of our model and join our open source projects. And here comes to the ending of this talk. First, automating deep learning, deep neural network design, and also deployment is crucial for Qualcomm AI research. We've been conducting leading research on this part and trying to deliver a high accuracy model with much compressed solution. And we try to open source as much as we could and try to let as many people use as possible. Right. That's the end of my talk. Thanks so much for attending.
Thank you so much, Dave. Questions, please?
Hi, thanks for the presentation. Regarding the NAS, the DONNA part, so how do you divide the network?
Oh, yeah.
How do you choose to try?
So let me go back all the way. It's kind of far from here. So currently, it's simply based on number of the output channel of each block. For example, if you can see here that channel 32, channel 64, channel 96, so on and so forth, we use each of, whenever there's a channel change, we consider that as a block. That's what we currently do. Oh, yep.
Hi, good presentation. For the DONNA NAS as well, it seemed like the big advantage was that it was hardware specific and the cost. And so when you do this for a specific chip and then you want to get this model to run on another chip and the software's changed a little bit, how much effort is involved to go and bring that model to a new chip?
Oh, thanks for the question. So yeah, I think that's a good question, and also I think that's also one of the contribution in this work. So the good thing is that we don't have to, if you have a hardware change involved, you don't have to retrain the BKD library. You can, like as shown here, you already have a pre-trained BKD library, and somehow if you want to deploy onto different devices, you simply just swap your new device constraint into the evolutionary searching part. And this evolutionary searching is very, almost zero cost. It can be done in just CPU and on the target, and also on target inference, right? So this part is basically zero GPU cost. And therefore, yeah, so this is whenever it comes to a target change, you can reuse as much as you can and simply swap the target inference. Yeah. Thank you.
One question from my side.
Sure.
What opportunities do you see in reducing the bit depth to less than 8 bits?
What opportunity? Right. So this is the one of the hardest part, because most of the quantization and auto-quant you see here, it's easy to achieve 16-bit or 8-bit mixed precision. But when it comes to lower than 8-bit, it has to be a certain hardware support as well. So right now it's still challenging to have such simulation, because there's not all the hardware, for example, IoT devices or MCU support 4-bit simulated inference. So this is like ongoing work, I think. Yeah.
Okay. Thank you.
Yep.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Sentient. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. Gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of silver sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Grovity, Hymix, HOTG, Imagimob, ITMIS, Lattice, Nota, OmniML, PixArt, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texel, and Google. So we are very thankful for their support, and more importantly, for them being part of this community and driving it forward.